Hello, precious one. I welcome you once again to Kenya Mathematics Classroom. Today we are looking at the continuation of rational functions. And if today is the first time you are watching me on Kenya Mathematics Classroom on rational functions, I would advise that you go back to the platform Kenya Mathematics Classroom to watch my presentation on rational functions, the general idea, the beginning of the rational functions in part one, so that you appreciate what I'm going to do now. In the part one of these rational functions, we are looking at rational functions in general. We have also looked at addition of rational functions, subtraction, multiplication, and divisions of rational functions. So I would advise that you refer to part one of this rational functions presentation so that you can appreciate what I'm going to do here. You can appreciate what I'm going to do here. Now, this is a continuation of the rational functions, and now today we are going to look at what we call partial fractions. We are going to look at what we call partial fractions, also under rational functions. Now, there is something I want to explain to you so that you appreciate these partial fractions. Let's assume that you have 2 over 3 plus, and you have 4 over, let's say you have 4, or let's say we have 3 over 4. Okay, 2 over 3 plus 3 over 4. Now, if you are simplifying this, if you are given this to simplify, this will be because you have to find the LCM. And the LCM of 3 and 4, it will be 12. Now, when you refer to my videos on addition of fractions, you understand what we are talking about here. So, now 3 into 12 is 4 times. Then 4 times 2 will give us 8. Then 4 into 12 is 3 times. 3 times 3 will give us 9. So, this will be equal to 8 plus 9 will be 17 divided by 12. Now, realize that 2 over 3 plus 3 over 4 can be simplified in this form. So it also means that 7 over 12 can also be simplified also in this form. So this is what we call the partial fractions of this. That's what we are talking about. This is what we call the partial fractions of this. So these are different partial fractions. When we put them together, we are getting this. So we can also split this into this form. That is what we are going to talk about. And if you understand what is happening here, then this will be very simple for you. So in general, if you have 2 over 3 plus 3 over 4, we simplify. The LCM is 12. 3 here, 4 times. 4 times 2 is 8 plus 4 here, 3 times. 3 times 3 is 9. Then 8 plus 9 is 17. Divided by the denominator. That is 17 over 12. So you can simplify this to get this. And this can also be split into 2 also to get this. Now, how to simplify this in this form is what you are going to look at. And that's what we call the partial fractions. And that's what we call the partial fractions. Now, before we also start the partial fractions, I want you to understand the difference between what we call an equation and what we call an identity. Now, when we talk about an equation is an expression that is true for specific values of x, but an identity is an expression that is true for all values of x. I will explain this to you in no time. Now, let's assume we have 2x plus 4. Let's assume that you have 2x plus 4 is equal to 10. If you have 2x plus 4 is equal to 10. When you look at this is an equation because this is true for specific value of x. Now, when you have to solve this, it means that find the value of x. Now, x is a value. When you multiply that x by 2 and add it to 4, you are getting 10. So if you want to solve for this, you subtract 4 from both sides. And when you refer to my presentation on linear equations, you understand what I'm talking about here. So you subtract 4 from both sides. So you subtract 4 from the left. And whatever you do to the left, you make sure you do the same thing to the right-hand side of the equation. Now, 4 minus 4 is gone. So we have 2x on the left-hand side. And 10 minus 4 will also give us 6. Now, don't forget that we are now solving for x. But there is a constant attached to that x. So to find for x or to solve for x, you need to divide both sides by the constant attached to the variable you are making the subject. And we have 2 attached to this. So 2, we divide both sides by 2. So the left-hand side by 2, right-hand side by 2. Then our x will be 2 goes into 6 is 3 times. So the value of x is equal to 3. That means that this equation is true for only x equals 3. Apart from that, it will not be true for any value of x again. So when you talk about equations are expressions which is true for specific values of x. But with identity, they are true for all values of x, and I'm going to explain that. Now, let's assume that we have x plus 2 square equals x square plus 4x plus 4. If you are given this is an identity. This is true for all values of x. What am I talking about? Now, when x is equal to 1, let's look at what's happening. Then you are going to have 1 plus 3 square on the left hand side. Then you have 1 square, we have 4 times 1 plus 4. So if you want to simplify, then 1 plus 3 is 4. 4 square will give us 16 on the left hand side. Okay, so let's simplify the right hand side and see. We simplify the right hand side and see. So we have 1 square, and 1 square will give us, okay, don't forget, please, it's x plus 2 rather. So if x equals 1, then it's supposed to be 1 plus 2. Okay, so it's 1 plus 2. That means 1 plus 2 is 3, and 3 square will give us 9. So 9 on the left. Then let's simplify the right. So we have 1 square, that is 1, plus 4 times 1 is 4. So 1 plus the 4 is 5. Then 5 plus 4 is also giving us 9. So you see that the left is equal to the right when x equals 1. Now let's try for x equals 2. If x equals 2, the expression is x plus 2 all square. So x is now 2. So 2 plus 2 all square is equal to, then x square will now be 2 square. Then 4x will now be 4 times 2 plus 4. So we simplify the left. 2 times 2 is 4. And 4 square will give us 16. Now we simplify the right. 2 square is 4. 4 times 2 is 8. Then 8 plus the 4 will give us 12. And 12 plus 4 will give us 16. 12 plus 4 will give us 16. So you see that the left hand side is equal to the right hand side. Now when x equals 1, we had 9. When x equals 2, we have 16. Now when you put x equals 3, you can try that and see. Realize that the value you are getting on the left hand side will be the same as what you are getting on the right hand side. So every value of x you take, your left hand side of the expression will be equal to the right hand side. So this is what we call an identity. It's true for every value of x, all values of x. But this type is what we call the equation. It is true for specific values of x, and that's what we are talking about. So in general, that is the difference between an equation and an identity. Now, with the partial fractions, we are going to consider a lot of identities so that you appreciate what I'm talking about here. So we continue with our partial fractions. And with the partial fractions, we have types. We have denominator with linear factors. We have denominator with quadratic factors. We have denominator with a repeated factor. Then we have the improper fraction. These are the 4 types we are going to look at as far as partial fractions in rational functions is concerned. So we will look at the first type. And the first type is denominator with a linear factor. Okay, so when we say with a linear factor, then we are trying to say that the factors of that rational function, the denominator, as linear factors. So a rational function is said to be a denominator with a linear factor if the factors are in the form ax plus b. So take note of this. It's very important. This is a linear factor. So a rational function or a partial fraction, when you are given the expression, when you look at it, you could tell whether it's a linear factor, a quadratic factor, a repeated factor, or an improper fraction. Now take note that the denominator with a linear factor, denominator with a quadratic factor, denominator with a repeated factor are all proper rational functions. They are all proper rational functions. That means that the degree of the numerator must be less than the degree of the denominator. So take note of that. Now I will explain what I'm saying. So with the denominator with a linear factor, the factors can be expressed in the form ax plus b. But now with the second one, that is denominator with a quadratic factor. If it's a quadratic factor, then one of the denominators can be expressed in the form ax squared plus bx plus c, where a is not equal to 0. So this is a quadratic expression. So if one of the factors of that rational function, the denominators, can be expressed in the form ax squared plus bx plus c, where a is not equal to 0, then that expression is a denominator with a quadratic factor. So you have to understand that. I will explain this into detail so you get it. Now, then we also have denominator with a repeated. We have denominator with a repeated factor. Denominator with a repeated factor. And that one, if one of the factors can be expressed in the form ax plus b all squared, then that expression will be denominator with a repeated factor. So take note, if the factors can be expressed in the form ax plus b, then it is denominator with a linear factor. If one of the factors can be expressed in the form ax squared plus bx plus c, where a is not equal to 0, then it is denominator with a quadratic factor. But if one of the factors can be expressed in the form ax plus b all squared, then it is denominator with a repeated factor. Now, with the fourth one that is improper, we are saying that with the improper fractions, the degree of the numerator must be equal or greater than the degree of the denominator. If it happens like that, then that one will be improper fractions. And there are rules for that, and I'll teach you that when we go to the improper fractions. So take note that the first type, denominator is a linear factor. The second type, denominator is a quadratic factor. And the third type, denominator with a repeated factor, are all proper rational functions. Are all proper. When I say proper rational functions, then I'm saying that the degree of the numerator must be less than the degree of the denominator. Then when the degree of the numerator is equal or greater than the degree of the denominator, then we have the improper fractions. And I'll teach you that. So take note of that. Take note of that. So these are the four types we are going to look at. Denominator with a linear factor. We have denominator with a quadratic factor. Then we have denominator with a repeated factor. Then we have the improper fractions. Then we have the improper fractions. Okay, so let's assume that we are given, let's say 7x over x plus 2, then we have x minus 1 to express impartial fraction. To express this impartial fraction, what we look at, you have to check the denominator. That's the most important thing, because we have denominator with a linear factor, denominator with a quadratic factor, denominator with a repeated factor, and improper fraction. So our concentration is on the denominator. Now, when you check the denominator, we have two factors. You realize that we have factor x plus 2, we have another one x minus 1. These are two denominators, and they are all linear factors. You can see that the degree of the factor here is 1. The degree of the factor here is 1. And that makes it a linear factor, because we said that for the linear factor, the factors must be expressed in this form. That is ax plus b. And that is the form you are seeing. So this is denominator with a linear factor. And if it's a denominator with a linear factor, then this one has partial fraction. It will be a over the first factor is s plus 2. Then this will be b over the second factor is s minus 1. So take note of that. Then we will simplify. But I just want you to understand how to get the partial fractions. Then we will solve for a, then we will solve for b. That one I will teach you later. But for now, I need you to understand this. Now let's assume that, so this is assumption 1. Let's assume that we are given the expression 7x over x squared plus 2. Then we have x minus 1. Now when we look at this, you realize that one of the factors is quadratic, because we said that for the quadratic, one of them must be expressed as ax squared plus bx plus c, where a, that's the coefficient of the square term, must not be equal to 0. So when you look at x squared plus 2, you realize that we have an x squared term, but there is no x term, but there is a constant of plus 2. So this is still quadratic. So when one of the factors is quadratic, then it is denominator with a quadratic factor. So if it behaves like that, then this should be equal to ax plus b over the quadratic factor, that is x squared plus 2, then plus c over the linear factor, that is x minus 1. And we will simplify this to find for a, b, and c. And I will explain that. You will get it. You will get what I'm saying. Now, assuming that this is rather 7x over x minus 1, then we have x squared plus 2. Take note that when you look at this, the linear factor comes first before the quadratic factor, but still it is denominator with the quadratic factor because one of the factors is quadratic. And this one will have a partial fraction. It will rather be a over the linear factor, then the quadratic factor will be bx plus c over the quadratic factor. That is x squared plus 2. So the difference between this and this is the position of the quadratic factor. If the quadratic factor comes first, then the expression will be ax plus b over that plus c over the linear factor. But if the linear factor rather comes first, then it will be the partial fraction will be a over the linear factor plus bx plus c over the quadratic factor. Now, let's assume, I just want you to understand what is happening. Now, if you have 7x over, then we have x minus 1 here, then we have x squared plus 2, then we have another factor, x plus 2. Then this will now be equal to, take note that we have 3 factors now. Out of the 3 factors, 2 of them are linear, but 1 is quadratic. So the partial fraction will be a over the linear factor, x minus 1. Then because this is the quadratic, this will be bx plus c over the quadratic. That is x squared plus 2. Then plus d over the other linear factor. That means that with this expression, we are going to find a, b, c, and d. So in general, that is what is happening. So we have, when the factors are linear, then you have a over that plus b over that. If there is another factor, then it will be c over that in that order. And this is what we have. Now, let's look at, if we have 7x over, then we have x minus 1, then we have, let's say we have x plus 2 all square, x plus 2 all square. So if you have this, you realize that one of the factors is a repeated factor. It's a repeated factor. This is linear, but this one is a repeated factor. So this will be, the linear will be a over the linear factor x minus 1. But this is the repeated. So this will be b over what we have in the bracket is x plus 2 without the exponent 2. Take note of that. Then plus c over the whole expression. That is x plus 2 with the exponent 2. That is the difference. So if the 7x over x minus 1, x plus 2 all square, then this will be equal to a over the linear factor plus b over the expression you have in the bracket. That's x plus 2 plus c over the whole expression with the exponent. Then we simplify for a, b, and c. So take note of that. This is very important. This is very, very important. And take note, this could have also been 7x over x minus 1. Then we can also have x squared plus 2, x squared. I don't want to confuse you, so let me get this off. But take note, I want you to understand this. So this, we have the linear factor, we have the quadratic factor, we have the repeated factor. Then we will also look at the improper fraction. Now with the improper fraction, you need to, now take note, when you look at this, realize that the coefficient of the degree of the numerator is 1. That's the highest exponent. But this one, when you simplify, there is 1 here, 1 here. When you simplify, this will give us a quadratic expression. It is not a quadratic factor, but I want you to check in terms of degree. An x here, an x here. So the degree here will be 2, but the degree here will be 1. You see that it is linear factor. Now, the degree here is 1, but when you multiply this and this, you are going to have a cube term here. So it's still linear because 1 over 3 is proper. Then when you look at the same example here, now when you look at this repeated, the degree of the x here is 1, but the degree of the x here, this will give us a square term here when you simplify this. And this will give us an x here. So x square term here, multiplied by an x term here, we are going to have a cube term here. So the degree here is 1, and the degree here is 3. You see that 1 over 3, we still have proper. But now with the improper fraction, let's assume that we have 7x squared plus 3 over, then we have x plus 2, then we have x minus 1. Now when you look at this, when you check the denominator, you realize that they are linear factors. When you check the denominator, you realize that they are linear factors. So you may be tempted to write a over x plus 2 plus b over x minus 1 and find for a and b, but no. The degree of the numerator here is 2. That's the highest exponent. When you multiply this by this, there will be an x squared term. So the degree is 2. You see that it is the same. If it is the same, then it is now improper fractions. And the way we are going to solve it will be different. So we multiply this by this to get a quadratic equation. Then we follow division of polynomial to simplify to get your quotient plus the remainder over the device. And I guess you understand. If you are confused what I'm saying, you refer to my video in polynomials and you get exactly what I'm talking about. So that is what we are going to do if it is improper fractions. When we start solving questions, you will now appreciate what I'm talking about. But for now, in general, this is what we call the denominator with a linear factor, denominator with a quadratic factor, denominator with a repeated factor, and the improper fractions. So when we start solving questions, you will appreciate what we are going to do. But that will be all for now on this particular episode. Till I come your way again on Kenya Mathematics Classroom, it's a bye-bye for now.